Welcome students once again in the class of topology, and as you know, nowadays we are covering the chapter of covering spaces, compact spaces, and in the previous video I have explained the concept of countably compact spaces and we have covered starting theorem of that, and now I am moving ahead with another theorem based on countably compact spaces, and the statement of the theorem is, write down the statement of the theorem first and then we will move on to the proof. The statement is, let X be a topological space, then every infinite subset of X has a limit point if and only if every countably infinite set has, set in X you can say, or subset of X you can say, infinite subset of X has a limit point. So what I want to say here, what the statement of the theorem is, it is saying that if a topological space X2 is compact, then if every infinite subset of X is having a limit point, then every countably infinite subset will also have a limit point, and converse is also true. That means if every countably infinite subset of X is having a limit point, then every infinite subset of X will also have a limit point. One proof is very easy, is straightforwardly direct, that if every infinite subset of X has a limit point, then every countably infinite subset will also have a limit point. Why? Because if a subset is countably infinite, then obviously it is infinite. And if it is infinite, then it is given that every infinite subset is having a limit point. So every countably infinite set, being an infinite set, will have a limit point. So one way is clear. Now go around the other way, converse. Suppose conversely, suppose every countably infinite subset of X has a limit point, then what we are to prove that? We are to prove that every infinite set also has a limit point. So we will take an infinite subset of X and then we will show that it has a limit point. So let A be an infinite subset of X. We know that every infinite subset has, or every infinite set has, a countably infinite subset. So this infinite set, suppose it is A, I have named it A. So this is infinite set A. So it must have a countably infinite subset. So let it be B. So let B subset of A be countably infinite. And we are given that every countably infinite subset of X is having a limit point. So definitely B is having a limit point. So this means then B has a limit point, say alpha. So now alpha is a limit point of B. And if alpha is a limit point of B, then for every open set G or Gn, whatever you want to name, for every open set containing alpha, G intersected with the deleted neighborhood of B, or you can say B without alpha, will have some elements of B. So that means since alpha is a limit point of B, therefore for every open set G, or you can say N, because basically we are to consider the neighborhood. So for every open set N containing alpha, we have N intersected with B minus alpha. This is not phi, because N contains at least one element of B other than alpha, because alpha is a limit point of B. From the definition of limit point of a set, we know that every neighborhood of the limit point must contain an element of the set other than alpha. So N intersected with B minus alpha is not phi. Now, from here you can have the proof in 2 steps very easily. Now, what is B? B is a subset of A. B is a subset of A. And if B is a subset of A, then B deleted the element alpha will be a subset of A deleted the element alpha. And if this is a subset of this, then intersection of this set with N is a subset of intersection of this set with N. What we have done, just intersected with N both sides. And this is not phi. This is given. So a non-empty set is a subset of this set. So that means this set is also non-empty. So this means A minus alpha and intersected with N is not phi. So that means every open set N contains at least one element of A other than alpha, and that proves that alpha is a limit point of A. So this means alpha is a limit point of A, and that is what we wanted to prove, that every infinite set has a limit point, and A we have taken as an infinite set, and now we have proved that alpha is the limit point of A. That means every infinite subset of X is having a limit point if the space is given the condition that if every infinite set is having a limit point, then every countable infinite set is also having a limit point. So this condition was holding, and we have proved the required result. And now we are moving towards another theorem related to countably compact spaces. So write down the statement of the theorem first. Let X be a countably compact space, then every infinite subset of X has a limit point. Indirectly, what we are going to prove? We are going to prove that every countably infinite set has Bolzano-Weierstrass property. So this theorem can also be asked in your examination in this form. Every countably compact space has BWP, Bolzano-Weierstrass property. So this is the theorem. It can be also stated like this in a single line. So it can be asked in your examination in this form. So we have to prove that if a topological space is countably compact, then in this topological space every infinite set will have a limit point. So we are going to start the proof of the theorem. Proof: let X tau be a countably compact topological space. So we have taken a countably compact topological space, and we have to show that every infinite subset of this topological space has a limit point. That means it is having Boson over such property. So we will take an infinite subset of it, and then we will show that the infinite subset what we have taken, so it is A, then we will show that A is having a limit point. So let A be an infinite subset of X. And now we have to show that A has a limit point. We know that every infinite set has a countably infinite subset. So we will take a countably infinite subset B of this infinite set A. So therefore there exists a countably infinite subset B of A. Let, since B is countably infinite, so members of B can be numbered, B1, B2, B3 like this. So I am naming members of this set B as B1, B2, B3 and so on. So this B is infinite as well as countable. Now B is a subset of A. Note that B is a subset of A. So that means B dash is a subset of A dash. B dash here is not complement of B, it is derived set of B. You can write D of B also. You can write D of B is a subset of D of A. You can have any notation. So normally I use dash for derived set. So I am writing B dash is a subset of A dash. We have to show that A has a limit point. Suppose on the contrary A is not having any limit point. If A is not having no limit point, that means A dash is phi, because A dash means derived set of A is the set of all limit points of A, and A is having no limit point, that means A dash is phi, and B dash is a subset of A, so B dash is also phi. So this means your B dash is phi. And you know that B bar, that means closure of B, is B union B dash. This is a theorem in the first or second chapter in the topology. And here your B dash is phi. So if your B dash is phi, then what is your B bar? Your B bar is B. Closure of B is same as B. If a set equals its closure, then the set is closed. So this means B is closed. So B is a closed set. One thing. Second thing, B is having no limit point. That means for every xn belonging to this B, I have named B1, B2, instead you can have, to be more clear, let it be x1, x2, x3 and so on. For every xn belonging to B, xn is not a limit point of B, because B is having no limit point. So for every xn belonging to B, xn is not a limit point of B. And if xn is not a limit point of B, definitely there will exist an open set. There will exist an open set Gn containing xn, such that Gn intersection with B is a singleton set xn, because it will have no point other than xn, because xn is not a limit point. So there must exist an open set Gn satisfying this condition. So that means for x1 you will have G1, for x2 you will have G2, for having x3 you are having G3 and so on. For each xn you are having one Gn. So that means this collection Gn, where n is any natural number, this collection C is a countable open cover of B, because for every member xn of B you are having one Gn. So G1 will cover x1, G2 will cover x2, G3 will cover x3, G4 will cover x4 and so on. Union of all these Gns, that means the members of C, will cover B. So your B is subset of union of all Gns n belonging to n. And now what you have to do, just take union with B complement on both sides. So union with B complement here and union with B complement here. And a set B union with its complement is the whole space X. So it is your X. So X is a subset of this, or you can say X is equal to this, because X is the whole set, universal set. So X is covered by these sets. These sets means B complement and all Gns, where your n is a natural number. This is a countable open cover of X. This C1. So this means C1 is a countable. This is a countable open cover. This is a countable open cover of X. And X is countably compact given. So it must have a finite subcover, which is not possible, because here this countable open cover has no finite subcover. Why? Because in this collection, this B complement will not cover any part of B. So the part of B will be definitely covered by Gn. And if you are to find a finite subcover, then definitely you will have to remove a countable number of members from this collection of Gn. But you cannot remove even a single Gn from here, because if you will remove suppose G2, then X2 will not be covered. So it will not be a subcover. If you will remove G4, X4 will not be covered. If you remove G5, X5 will not be covered. So this countable open cover of X is having no finite subcover. That means your X is not countably compact, which is a contradiction. And this is a contradiction because our supposition was wrong that A has no limit point. A must have a limit point if the space is countably compact. So here we have finished this theorem, we have completed this theorem. Here I am going to stop this video. In the next video we will have more and more theorems on countably compact, and then we will start sequentially compactness and locally compactness. Till then, thank you once again.